Hi everyone, and a warm welcome to my workshop here in Sheffield, England. Remaining with an overseas theme, I have, for repair only, a Radialva model Superbutt or Super BUT 5-valve AM radio manufactured in France sometime during 1954. I haven't as yet removed its back cover, which looks to have been attacked at some time with a butcher's knife. So I know as much about this radio as you do, but I have a circuit diagram and tools at the ready. So I'll lift it onto my bench and I'll get started. As already mentioned, here is the Superbutt or Super BUT by Radialva. It's a French radio bought earlier last year, May 2019, from an auction house. From the outside appearance it is not in sparkling condition, but I have to point out I have tattled a lot worse. Looking at the dial, this radio looks to be long wave, medium wave and 2 shortwave bands. The plastic around here looks to be very tarnished. There don't seem to be any tobacco odours, and there is a crack just here left of the speaker grill. There is an electrical safety test sticker on top, just here. It clearly states this radio has failed, and as a consequence it is not to be used, despite the fact that that might be good advice. I'm definitely going to disregard what this sticker is recommending I do. Right, I'll turn this radio around and we can have a look at the back. For some unknown reason, a previous owner has been cut in 1 or 2 corners. Why is beyond me. Since I don't speak French and I can't say what is printed on this back cover, I'll go ahead and remove it so we can see what it looks like internally. Right. Right, just put this somewhere safe. Right. I don't see a mains lead. I guess it's been severed. There are plenty of long-legged spider carcasses. It's dusty, but not overly dusty. Give me a second or two to liberate this chassis from this cabinet. As you see, this radio is a 5-valve. 1, 2, 3, 4 and 5. It has a decent sized electrical speaker. Before taking a look at the underside of this radio, I'll prevail upon my wife to vacuum clean the dust off this chassis. Wifey never fails to perform a decent dusting job on my radios. As can be seen, there is a fair amount of discolouring on this chassis. I don't dislike it. It has the patina. Right, I'll turn this chassis over so you can see its underside. Right. This is what is left of its mains lead. It also looks as though the main switch has stopped working. Connection from the mains input looks to be bypassing the main switch, and is connected direct to the primary of the mains transformer. Off camera I'll take a deep dive into this slot here and see what's going on. First and foremost, when servicing vintage electrical equipment, or any equipment for that matter, be equipped with service data. This, such as its general quality, is the circuit diagram for this Superbutt radio. So what is the strength of this so far? Well, having checked the volume potentiometer, I find that it is reading OC. There it is. As far as I'm concerned, it is the end of the road. So in the trash it goes. It will be replaced with this old new stock 1 meg log potentiometer and switch, along with a replacement length of mains lead. And hey presto, the 1 meg log potentiometer with double pole single throw switch is replaced, just the way you expect. The next port of call is the reservoir and smoothing electrolytic capacitors. This model of radio, being introduced onto the French market sometime during 1954, the year I first saw the light of day, its original electrolytic capacitors, as well as its non-electrolytic types, are in place. Given that, it's high time they, that is, all values over 1 nanofarad, are replaced. Since there is not a great deal of space just here to mount a printed board, I will place new electrolytic capacitors inside the old emptied canisters. As you know, I don't normally go in for stuffing new capacitors into empty canisters, but purely for the sake of convenience, I'm always prepared to make a few exceptions. I'll remove this electrolytic capacitor here, then I'll get back to you. Okay chaps, one 40 microfarad reservoir electrolytic capacitor liberated from this chassis. This 47 microfarad electrolytic capacitor will hopefully fit inside the original canister. If not, I do have others to hand. I've made a start at unfolding the aluminium around its base. We have to exercise great care in instances like this, since the Bakelite fixing base can easily break. I'll do some more, then I'll get back to you again. That's the Bakelite fixing base liberated in one piece. As you see, the new 47 microfarad electrolytic capacitor goes into the old electrolytic capacitor canister, but it is a snug fit. I'll solder the required leads, reassemble and refit it onto the chassis. Here we go chaps, one capacitor for the use of. And now it's turn for the 35 and 5 microfarad capacitors. It suddenly occurred to me, as I was about to start opening up that 35 and 5 microfarad dual electrolytic capacitor canister, it was far easier, and with less debris, to mount the 2 new electrolytic capacitors direct onto this radio circuitry. And I've done just that, and it's made for a fairly neat job. Why make extra work when there's no need to? I've returned the original dual electrolytic capacitor canister to this chassis, just there, and it has at least filled in what might have been an unsightly hole if I'd have left that capacitor off this chassis. Okay, now I'll go on to replace non-electrolytic capacitors that are valued over 1 nanofarad. And what might appear to be no longer than the flick of a light switch, or the capacitors, valued above 1 nanofarad, have been replaced. In reality, replacing the old capacitors took almost 1 hour. Certainly a generous 3/4 of an hour. As you will see, most of these old paper and foil capacitors have been puking up their ring piece. One there. One there. Another one there. Another one just there. Their paper dielectric will very likely be in an advanced state of decay. Therefore, electrically leaky also. As a consequence, it's time for them to be put out to grass, or more accurately, put into the trash bin. Next on the to-do is check the strength of each resistor. Each one might look good, but appearances can be deceptive. Personally, I prefer to take nothing for granted. Back shortly. I've tested all the resistors, starting from the front end, associated with the ECH81 frequency changer and local oscillator, on through to the EBF80 IF amplifier. Now, out of those resistors, I found one hopelessly out of tolerance and another reading as OC. I'll go into a little bit more detail in a short while. In the meantime, I'll continue checking. I'll get back to you after I've checked the strength of this wee lot here. No sooner said than done. Each and every one of these resistors checked out fine. Certainly well within their 10% tolerance ratings. Before applying mains power to this radio, yes, before powering this lot up, I'll install this wee fuse holder onto the back part of this ironmongery. It shouldn't take too long to do. I'll be back once that wee task is complete.
Forecast issued by the Met Office.
And here is one Radialva Model Super BUT vintage radio brought back into operation.
German Bight, Humber, Thames, Portland, Plymouth and South East Iceland.
Plenty of volume there.
Midday. High southern.
There's not going to be too much on on short wave. It's a little too early in the evening. Well, there's certainly not a great deal on that particular shortwave band, but then I don't expect there to be. I'll put it back onto long wave, long radio 4.
Showers, good. Monday, Fastnet, Irish Sea. East or northeast, 4 to 6. Showers, Good. Shannon, north or northeasterly 4 or 5.
I'll hasten to add I am very pleased with its general performance.
Rockall,
From time to time I ponder over the billions, if not more, old radios that have been incinerated and ended up in landfill.
good.
What percentage of them could have been made serviceable?
Fair. Good.
No doubt a good number were working
4 to 6.
when they were discarded.
Good. Occasionally
Take all the vintage radios repaired and restored on
variable 2 to
YouTube,
6.
for instance.
Good.
In effect, most, if not all of them, should be good for at least another 10 to 20 years.
Good. Occasionally moderate.
Doubtfully, any one of the electronics designers, electronics goods manufacturers, retailers, and consumers for that matter, could have imagined any one of their products would be serviced and restored in, say, 50 years' time. Being restored to good working order in the 2020s would have been seen as a silly joke, to be laughed and poked fun at. But here we are, we the vintage radio men. I'm not aware as yet of vintage radio women repairing and restoring what are, in a few instances, radios that would not have been considered worth looking at some 50, 60 years ago. This radio, for instance.
But elsewhere across the British Isles, we're looking at lows down around.
What was required to get it working once again?
Down to -6.
A few capacitors that would easily rest in the palm of one of my hands, 3 resistors, wire, heat shrink, fuse, fuse holder, and a little bit of know-how. Certainly not much more. And as I have said earlier, I'm satisfied with the performance of this radio. Right, it's now over to the circuit diagram. And now it has come to that time when I give my brief outline of this radio circuit diagram. Doubtless it will be boring and tedious for some and be of great interest for others. If you wish to skip this section, then please do so. I appreciate theory is not everybody's cup of tea, but for me it is equally as interesting as the practical. I will, however, whiz through the theory at breakneck speed, so hold on to your hats. In my usual fashion, I will begin at the power supply circuit, and having gone through each stage, I will stop and come up for air once I've stopped at the end of the AGC line. Now, you will observe the general quality of this circuit diagram is not all that clear. Every possibility, it is a copy of a long line of copies. I have downloaded a better quality copy onto my iPad. Just there. Since it is fairly small, it might prove tedious to follow. Right. I'll manage with this paper copy. Perhaps I'll use my iPad version to clarify poorly printed component values, etc. We'll see how things turn out. Before launching into this, I'll briefly point out, as a reminder to anyone who is unclear, there are lethal voltages associated with vintage valve equipment. If there is any doubt, either leave well alone and pass restoration work over to a known bona fide time-served electronic service technician, or seek training and mentoring from I said bona fide technical person. If you are following along, you are doing so at your own risk. Doubtless you are aware this is a 5-valve, 4-waveband superheterodyne receiver. Its power supply circuit is fairly conventional. Its mains transformer has 5 mains voltage tap-ins, the lowest input being 110 volts and the highest is 250 volts. Required operating voltages are induced into the mains transformer secondary windings. Full wave rectification is achieved via the EZ80. From the EZ80 cathode, around 230 volts DC forms the HT rail, of which its first filter is achieved via a 40 microfarad capacitor, since replaced with a 47 microfarad electrolytic reservoir capacitor. The mains transformer high voltage secondary, supplying voltage to the two anodes of the EZ80, has a centre tap. By doing so, this arrangement provides full wave rectification for this radio's power supply. Rather than the centre tap being strapped directly down to deck, there is a choke auto transformer effect. I say transformer effect since there are 2 tap-ins that come directly off it. The one furthest away from deck provides negative bias for the grid 1 of the EL84 audio output pentode valve, and the one closest to deck provides bias on the negative diode section of the IF amplifier. But there's more. Let's go back to the HT rail again, starting from the top of the 47 microfarad reservoir electrolytic capacitor. Follow up the trace and turn left. Here we see a pi filter circuit incorporating a 47k resistor and a 5 microfarad electrolytic capacitor. I've replaced that 5 microfarad capacitor with 4.7 microfarad, and its negative end is strapped directly down to deck. Now I'll return to that in a short while. Continuing a little further to the left along the HT rail, taking the next right hand turn up towards the primary winding of the first IF and voltage supply to the EBF80 IF amplifier anode, we see there is a 35 microfarad electrolytic capacitor. I've replaced it with a 33 microfarad. Just one moment. Incorporating a pentode for the first audio or preamplifier purpose is somewhat unusual. Those types of circuit are often associated with double diode triode valves. Due to the position of grid spacing within pentodes, they can be somewhat noisy. Now, from the 1 meg log volume control, just there, the demodulator signal or audio content passes through coupling capacitor are 22 nanofarad, and it goes up onto grid 1 of this valve. This 10 meg resistor just here is therefore leak or draining purpose. Its cathode is strapped directly down to deck, and I've touched on the voltage on grid 2 and also mentioned, though there is voltage on the anode, AC signal content shares the same line as the HT. There's also on that line a 22 nanofarad capacitor that is coupling, and from there is a stop resistor, and its purpose there is to stop any oscillations or certain stray frequencies when it is fed into the grid 1 of the audio output valve. Remaining with the HT rail, I'll do a 3-point turn and start heading back towards the T-junction that comes off the 47 microfarad reservoir capacitor, and continue on and pay the EL84 audio output pentode valve circuit a quick visit. You will notice that its grid 2 has full HT potential, and also the primary of the audio output transformer, which is also the load for the anode of the EL84, and that particular line there, or HT. Not only can we have DC, but also there is AC content as well, which coexists on that line. It is low current, but when inductively passed across onto its secondary, the voltage is reduced, but the current is raised, thus giving ample scope to drive the speaker. The 22 nanofarad that is in parallel with this transformer's secondary is the top cut or tone correction. It also helps to suppress certain oscillations or frequencies associated with the anode of the EL84 valve. You'll also notice that grid 1 is bias for this valve. Its cathode is strapped directly down to deck. But then there is this device here, which I mentioned, which also adds to extra biasing. Purely for ease, and also being conscious of the time factor, I'm not as far on as I intended. I'll omit the feedback circuitries associated with these valves, or the audio output, and I'll move over to the preamplifier, or first audio stage associated with this EBF80 double diode pentode valve. Jumping across to the front end, included towards the bottom left hand corner of this circuit diagram is a rectangle in which is printed block de accord. Part contained within that block diagram are the two ferrite rod aerial arrangements. And here we go. They receive the entire spectrum, at least in theory, according to the band they were designed and manufactured, which is long wave and medium wave, or in other words, each coil, along with its associated capacitances, etc., is resonant with its designated band or frequency range. The station frequency, in accordance with its band, feeds into grid 1 of the ECH81 triode heptode frequency changer. In addition to the long and medium wave bands, there are two short wave bands from an external aerial fed in just at the back here. Modulator signals inductively pass through LC bandpass filtering circuits that also feed into grid 1 of the ECH81 via a band selection switching arrangement. Okay, comparing the heptode section of the ECH81 frequency changer to a cement mixer, in other words, it mixes what is put into it, those signals are amplified, though not in any prolific way. From the heptode anode, there are a multitude of signals or frequencies, but we are only interested in listening to one station at a time. Returning once more to the blocked accord rectangle, the local oscillator or LC arrangement is also included. How do we know that? Well, note the connections drawn between the triode section of the ECH81 and the block diagram in this rectangle. Addition to those, the biggest giveaway by far, or at least it is to me, are the ganged tuning capacitors. The intermediate frequency, or IF, of this radio, being fixed at 455 kHz at the heptode anode, so there, is both the station frequency, the IF frequency, as well as the sum and minus of those two frequencies. Of course, as mentioned, there are loads of other frequencies present at that point, but the frequency of interest is the 455 kHz IF, along with the station frequency content. So, in effect, when the tuning knob is rotated and the dial cursor glides to and forth over the dial, the station frequency and the 455 kHz frequency are tracking. In other words, the IF frequency is always in front, or in addition to the station frequency. Now the 455 kHz IF frequency is effectively filtered by the first IF transformer as well as the second IF transformer. There are a few decoupling capacitors that provide stray or unwanted harmonics, etc. A passage down to deck. The IF frequency is inductively coupled to its secondary winding, and from there it is fed into the grid 1 of the EBF80 IF amplifying pentode. You will observe this amplifier circuit is not as complex as other circuits incorporated into this radio. It's rare that they are. They do exactly what is written in the radio manuals. They give the IF frequency its final push, In other words, the IF amplifier amplifies the signal prior to demodulation. Now, prior to that demodulation, the 455 kHz IF signal, which passes inductively through the second IF transformer, feed into the diode anodes, which are strapped together. In effect, they are in parallel. So, demodulation, which is nothing more than rectification, is taking place. That being, of course, creaming off the audio content from the modulated or AF frequency, which, as it would stand prior to demodulation, the top half of the signal would cancel out the bottom half of the signal. A rectifier, being forward bias, conducts on the positive half of the modulated IF signal, but does not conduct on the negative half, thus leaving the top half. Therefore, there is nothing to cancel out. So the audio content, which is, let's move these out of the way, which, as I was saying, oh yes, which is filtered just here prior to it being fed into the volume control. No doubt some might feel relieved to hear we have now come to the final part of this short theory section. As you will doubtless be aware, super heterodyne radios incorporate a signal strength governing circuit that is known either as the AGC, or automatic gain control, or as the AVC, that is automatic volume control. I tend to refer to it as the former because I'm what might be described as old school or old-fashioned. If you recall what reception can be like when listening to stations on a TRF or tuned radio frequency receiver, signal strength fluctuates and selectivity can very much be compromised. Shortcomings of those sort have largely been overcome thanks to the super heterodyne receiver. Now, if we compare the effects upon the AGC line with respect to the signal strength, voltage will be less negative when signal strength is weak. Therefore, the ECH 81 grid 1 and the EBF 80 grid 1 bias being less negative will cause those valves to conduct more or work a little harder. Consequently, signal amplification will increase. Conversely, in the event of stronger signals, voltage on the AGC line will increase in negativity. Therefore, grid 1 pertaining to those two front-end valves will react accordingly, and signal amplification will reduce as a consequence. Since there is a time constant element on the AGC delay line in accordance with a capacitor, which in this instance has a value of 100 nanofarad. Now, if the value of that capacitor was reduced, say, to 10 nanofarad, the delay response time would narrow or reduce the delay time. The effect would be an erratic AGC line. Conversely, if that capacitor value was increased, say, to 680 nanofarad, the delay time response would broaden. Therefore, the effect would be a somewhat retarded AGC line. So there we have it in a nutshell. Yes, it's all clever stuff. That's why we like it so much. Why anyone would have felt a need to cut corners, such as seen here, is beyond me. All I see here is what was once an intact rear and undercover, pretty much trashed by some previous owner. As can be seen, I have now begun the task of putting right what was put wrong. Doubtless some of you have heard me say in past videos, I have no problem with past servicing work. It does not bother me, provided it was done correctly and in an orderly manner. Unauthorised modifications, such as seen here, present a risk of danger. Electrical safety standards at the time this radio was manufactured, for example, was not as stringent as they are now. I therefore make no apologies for repeating myself when talking safety. Here is a clear case in point where safety, such as it was, has been undermined by what very much looks to have been a pair of untrained hands in this respect. This undercover has not only been severed from the rear cover, they were an integral part. There is now no provision for securing this undercover to this cabinet. It can now be easily removed, and if the radio is plugged into a main socket and switched on, there is a distinct risk of electric shock. Though a vintage radio incorporates a mains transformer, like this particular radio for example, if handled incorrectly it can easily be as lethal as a vintage AC/DC radio. Be aware, electricity kills. One of a number of reasons why I stress, if unsure, leave well alone and pass electrical repair or restoration work over to a known, time-served, bona fide service technician. If you are watching this video, you are doing so at your own risk. As can be seen, I have made the bottom right hand corner good once again. I have marked out this piece of stiff card ready for cutting and shaping, so I can do the same for the left hand corner. I'm pleased to report it started to take shape. A few minor tweaks here and there, and it will be time to get out the glue pot and adhere this wee sucker to the rest of this rear cover. So it will. As most of you know, I'm a belt and braces type of person. Whenever I've made, constructed or repaired something, I want it to last a few years. My repair of this back cover is a case in point. All I have accomplished here is putting right what was put wrong. I fashioned and fitted two corner pieces, and with a strip of thick stiff cardboard I've fitted the back cover to the undercover, in effect returning it to how it once was. In addition, I've fitted cardboard braces over where the corner pieces butt up to this back cover. Hopefully they should provide extra strength. It's now time to get started on polishing the cabinet. So I'll get back to you with a progress report in a short while. A lustre is starting to appear on this radio's cabinet. As I've mentioned in one or two of my past video uploads, preparation is the key to success. Several specks and splashes of white paint needed removing, along with 66 years of general grime. Once all of that had been accomplished, it was time to apply polish. Now, there are a variety of polish products suitable for this type of cabinet that are on the market. The product that I use mostly is Greygate plastic polish. No, I'm not sponsored by the manufacturer of this product. All I'm saying here is this is what I use. I'll now go on to apply 2 coats of wax polish to this cabinet, and it will be time to fit the rear cover. I'll return once that lot has been accomplished. And here we have it, chaps. This radio cabinet was polished with bry wax. I'm not sponsored, nor do I have affiliations with the manufacturer of this product. It is what I use to polish this radio cabinet. The front speaker grille and surround are not up to much. Over the years the plastic has become brittle and discoloured, and it has its fair share of airline cracks. That, of course, was the chief reason I only washed it and did nothing else to it. One day, when I'm able to afford a 3D printer, I'll hopefully try my hand at fabricating a replacement grille and surround. Until then, I'm prepared to live with it as it is. It's the only French radio I own. Alright, I'll just turn it around. Right, what can we say here? Well, as for the rear and undercover, it's a mess. But I've done what I could with it. It fits, it's safe, and it's strong. Those are the only attributes I can give to it. This radio circuit is fairly straightforward to follow. Using an EBF80 double diode Very HF pentode is a somewhat unusual choice for first audio or preamplification stage. I've never encountered that arrangement before, but it certainly works well. What you see here inside this green plastic bin are the capacitors and resistors that were replaced. Sealing the actual capacitor inside a glass tube is somewhat novel. Or at least it is to me. It was the first time I saw that arrangement. I like this radio very much. as I said a moment ago, it is the only French radio I own, so it will occupy a prominent place in my vintage radio collection. I will now go on to apply 240 volts mains to it and switch on. Starting off with the long wave band, this is BBC Radio 4. I don't know whether it will be visible on camera, but the dial cursor is where it should be.
Nobody thought that the risks were greater than the benefits.
As the years progress, the number of stations on this band continue to diminish. There are no stations to the right of BBC Radio 4.
And a picture might go for a second, or sometimes even a third.
There are very few stations to the left of Radio 4. There are more stations available on the medium wave band. How long they will remain so is anyone's guess. The emphasis is towards digital and online.
This mess around Article 16, but also
there's not a great deal towards the right of the dial on medium wave. The number of stations available on the shortwave band will increase throughout the night and into the wee hours of the morning. Depending upon the time of year, weather conditions, local interference, atmospherics, etc., shortwave bands, especially on domestic receivers like this one, generally start to become lively from around 2100 hours and continue to do so to around 0500 hours. Then they start to wind down. Or at least this is how it can be here in England, or this part of England where I live. Let's see, what time is it? Hang on. Oh, it's 2018. So, it is a little on the early side for shortwave listening. Yes, a decent performing radio. Should my videos be of interest, I cordially invite you to subscribe to my channel. That is, of course, if you have not already done so. There are more overseas as well as British radios requiring attention. I thank you for viewing this vintage radio repair video. Your time and interest is always appreciated. Until next time, I'm Phil, over and out.